Now we want to show that f of x is continuous. So what does it mean for a function to actually be continuous? Essentially, what it is that if we have some open set in the range, then the preimage of that open set must be open in the domain with respect to that function. And this is what defines a continuous function. And there's another formulation where we can take some open interval, say from c to d, in our range, which is from 0 to 1, and some point that is an element of this open interval. And if this function is continuous, then we should be able to find a neighborhood of x naught in the domain. We'll call it u x naught, such that the image of u of x naught is contained in this open interval in the range. And the reason that this works as a definition of continuity is that what this is essentially saying is for the preimage of c to d, and any point x naught in this preimage, there's an open neighborhood u of x naught contained in this set, which means since x naught was an arbitrary point of this preimage, that every point in this preimage is an interior point, which means that the preimage here is open. So this is the definition that we're going to go for. We're going to take some arbitrary point in this interval from c to d, and then bring it back to the domain and find an open neighborhood contained within the preimage, or such that the image of that open neighborhood is contained in our open interval. And we're going to use this these facts that we proved up here, so I'm going to bring this down. So we have that f of x naught is some point in this interval from c to d. So c is less than f of x naught, which is less than d, and we want to find an open neighborhood of x naught in the domain such that its image is contained as well in this open interval from c to d. So firstly, what we're going to do is we're going to use the fact that between any two real numbers we can find a rational number. So we can find two rationals, p and q, such that c is less than p, is less than f of x naught, which is less than q, which is less than d. And now we can use these two rationals to construct our open neighborhood because we defined our open sets for all the rationals in between 0 and 1. So what I'm going to say is the open set we want, that's a neighborhood of x naught, is going to be uq minus the closure of up. So now we want to verify that, well, firstly, let's note that this actually is an open set because we have an open set here minus a closed set. So really this is just the intersection of two open sets. And now we want to verify that this is indeed a neighborhood of x naught. And the way we do that is we show that x naught is an element of uq and x naught is not an element of the closure of up. So firstly, we have that f of x naught is less than q, right? So we can use the contrapositive here of number 2 to say that this implies that x naught is an element of uq. So this is good. And now we want to show this. And we have that f of x naught is greater than p. And then using the contrapositive up here, this implies that x is not an element of the closure of up. So this is good. And this is indeed a neighborhood of x naught. And what's left to show is that the image of fu is actually contained in this closed interval from p to q. And of course, this is contained in the open interval from c to d, which is what we were trying to show. So how are we going to do this? Well, we'll take x to be any arbitrary point in our neighborhood u, and then we want to show that f of x is less than or equal to q, but also is greater than or equal to p. So this will imply that f of u is contained in this closed interval, and then that's contained in the open interval. So we're going to start with this equality. We want to show that f of x is less than or equal to q. So we use our definition of u, and we say that if x is an element of u, then it's also an element of uq. And now this implies that x is also an element of the closure of uq. So because the closure of any set contains that set, and this allows us to use number 1 up here and simply say that f of x is less than or equal to q. So this equality is established. Now we want to focus on this other equality, or inequality. So we have x is an element of u, which implies that x is in fact not an element of the closure of u of p. And now since the closure of u of p contains u of p, we also have that x is not an element of up. And finally, this allows us to use 2 and say that f of x is greater than or equal to p. Thus, we have that the image of u is contained in the closed interval from p to q, which is contained in the open interval from c to d, and f is continuous. So we're done.